We are going to take a look at parts C through F of problem 1 of for 2022. I have a separate video for parts A and B, but you can watch this without having watched the previous one. Really, the key thing to know about this problem is that we have a table of h of x and h prime of x where all of these functions are defined and continuous at every point. Again, whenever you're given a table of values, you don't have much information about what's happening in between the table entries, but they are giving us an information in this problem by letting us assume that between the consecutive values of x in the table, h of x is either always increasing or always decreasing. Like, for example, between -4 and -2, we see that h of x has gone down. It went down from -0.5 to even more negative, -2. So we know h of x was actually decreasing here in between the table entries because they said we can assume this. But having pointed that out, let's dive into the question. What about part E? So part E and F, we're now dealing with left Riemann sum or maybe right Riemann sum depending on the question. But here we want to use the left Riemann sum, and we have 3 equal subdivisions to estimate this integral. So let's make sure we understand what the problem is saying here. So in general, how left or right Riemann sum works is as following. So here we have the x-axis, and we're going from -6 to 6. The fact that we have 3 equal subdivisions means we're dividing this into 3 equal parts. So we're partitioning this entire interval into 3 sub-interval, one like this, one like this, and one like this, with the same length. And now up above, our h of x, I'm not quite sure what it looks like, but let's say it looks something like this, h of x. And what we want is we want to estimate the area under this curve. Now, why would you want to estimate it? Maybe you don't quite know the formula for h of x, and even if you know the formula for h of x, maybe it's very difficult or even impossible to anti-differentiate h of x using, say, the functions that you know. So you want to just estimate the area using Riemann sum. And how we do that is we can either use the left Riemann sum or the right Riemann sum. Left Riemann sum, what we do is that for each one of the sub-intervals, we look at the left endpoint. So for the first interval, let's look at the left endpoint of -6, and we plug it into the function to get the height. And then you draw the rectangle like this. Now for the second interval, again, we look at the left endpoint, which is here. We plug that into the function. And we get this value out, and then now becomes the height of the second rectangle, like this. And again, for the third interval, we again look at the left hand point, we plug it into the function, and we get a rectangle like this. Maybe I'll quickly say what happens for the right Riemann sum. So again, given that we're dealing with the 3 equal subintervals again, and maybe this is your h of x. If we did right Riemann sum instead of left Riemann sum, then for each one of the subintervals, I'm going to look at the right endpoint. So for this one, I look at the right endpoint, I plug it in to the function, so I get this sort of rectangle. For this one, I plug this value into the function, so that's the height of the rectangle, and I get this. And for the last one, I plug in 6 into the function, and I get this sort of thing. And you see that we don't quite get the same thing, but both of them are giving you some sort of approximation for the actual definite integral or the signed area under the curve. So now how do you actually compute the Riemann sum? Well, we just want to find the area of these rectangles and sum them up. The width of the rectangle is often called delta x, since we're using x for the input here. So delta x is change in x, and each one gives you the width of the rectangle. So let's start by computing delta x. Well, the length of the entire interval from -6 to 6 is 12. So this is just the length of this entire interval. You just get it by doing 6 minus -6. In general, if I have integral from a to b, you do b minus a to get the length of this interval. And then we are dividing it into 3. So each delta x is going to be 12 or 3 or 4. So we know the length of each one of these width is 4. So now what about the height? Well, let's look at the first rectangle. We know the width is 4. The height, we plugged in the left-hand point, so we plugged in -6 into the function. So 4 times h of -6 plus, for the next rectangle, again, the width is 4, but now we plugged in -6 plus 4, which is the left-hand point of this interval, and -6 plus 4 is -2. And for the last one, we added another 4 to the left-hand point to get this left-hand point. So now we are at h of 2 here. So here we're going from -6 to -2, then -2 to 2 by adding delta x each time. So this is the Riemann sum that you want. And just for sanity check, you should make sure that you're adding 3 things. Because you have 3 subintervals, you should have 3 rectangles. So you should have one sum end for each rectangle. But you're not quite done. You actually want to plug in what h of -6, h of -2, h of 2 are, which are 2, -2, and 1. So going back down, we want 4 times 2 plus 4 times -2 plus 4 times 1. So this is our final answer right here. Make sure once you write things in terms of h, make sure you actually evaluate h of -6, h of -2, and so on. So bring it down all the way to numbers, and at that point you don't have to simplify according to the question. I guess one common mistake is to also write plus 4 times h of 6 here, because you might be thinking you go -6, then -2, then 2, then 6. But I mean, again, this makes no sense because you really want to make sure you're using 3 subdivisions, so you should be adding up 3 things. I guess we can also quickly do what happens when we do right Riemann sum. Well, in that case, you do, for the first interval, rather than picking -6 and plugging it into h to get the height, you'd be plugging in -2 and plugging it into h to get the height. So in this case, we'd get 4 times h of -2 for the first rectangle. Then for the next rectangle, you'd be plugging in h of 2 here to get the height. And for the final rectangle, now you'd be plugging in 6. So plus 4 times h of 6. And of course, you have to replace these with the numbers from the table. But if we do right Riemann sum, this would be the answer. Okay, so now let's take a look at the final part. Fill in each blank below with one of the following. So here on the right hand side, we have a bunch of Riemann sums. Let's actually be a little more careful. So what kind of Riemann sum is it actually? You're going from -6 to 0. So we're going from -6 to 0. And what are we doing here? We're looking at h of -6. We're looking at h of -4 and -2. So -4 here and -2 here. So this is the x-axis. And 2 here is of course coming from the fact that in this setup, our delta x is 2. So the width of each subinterval is 2. So what are we doing here? We're doing a Riemann sum with 3 subintervals. But more importantly, are we doing left Riemann sum or the right Riemann sum? Well, for the first interval, we're picking -6 to plug into h to get the height. And similarly, for the second and third one, we're picking the left-hand point. So this is actually the left Riemann sum. Let's similarly look at what's happening on the next part. For the next part, we're going from 0 to 6. And you're looking at h at 2, h at 4, and h at 0 here. So again, we see using the similar kind of interpretation, we're using 3 subintervals, and this is also the left Riemann sum. And now the question is asking, for example, for the first part, we're estimating this integral using the left Riemann sum. And the question is, are we getting an overestimate? If this is an overestimate, then this would be larger than the actual area that we want to find. Or are we getting the underestimate, in which case our approximation is smaller? Or maybe they're equal somehow? I guess that's possible when the function is maybe just a horizontal line or something like that, very basic. Or is there not enough information? And for this, let me quickly make a digression and give you some qualitative ways to tell whether a Riemann sum is an overestimation or underestimation. So here the key assumption that we need to make for this argument to go through is that h of x is monotonic on the interval. So by monotonic, I mean it's either always increasing or it's always decreasing. So yeah, let's first consider the case where h of x is increasing and see what happens here. If we do the left Riemann sum, so if I split up this interval into many parts and I look at the left-hand point to get the height, and I look at the left Riemann sum, and we sum up the areas of these, is this an underestimate or the overestimate of the actual area here under the curve? Well, here we clearly see that you get an underestimate. The sum of the areas of the rectangles is not quite all of the area under the curve. So here we get underestimate. And what about if we do right Riemann sum? So if we do right Riemann sum, then we are picking the right endpoint, so we get something like this, a picture like this. So we see that in this case, we get an overestimate. So I guess here we're using left Riemann sum, and here we're using right Riemann sum. So if our function is increasing and we use the left Riemann sum, then it's underestimate. If our function is increasing and we use the right Riemann sum, we get an overestimate. If the function is now decreasing, now the situation flips. So when I use the left Riemann sum, then you should be able to see that we get a picture like this, which gets you an overestimate here. Whereas when I do, say, a right Riemann sum, then I get a picture like this, and I get an underestimate in this case. So how you want to do it, as long as you know h of x is monotonic, so as long as you know it's like monotonically increasing or monotonically decreasing, then you just draw the picture. Just draw the picture and see whether you get an underestimate or overestimate, depending on the left Riemann sum or the right Riemann sum. Now, if h of x is not monotonic, if h of x is going from, say, like increasing to decreasing, and back to increasing or something like this, then qualitatively it's really hard to get any information on whether it's underestimate or overestimate just from left or right Riemann sum. Because parts of it you might have an underestimate and parts of it you might have overestimate, so you don't know which one is going to win out at the very end of it. So having that in mind, let's try attacking this question. So we know we have a left Riemann sum for the first part. So if we know h of x is monotonic, if we know if it's increasing or decreasing, then surely we can figure out whether it's underestimate or overestimate. So let's go back to the table and see what's happening between -6 and 0. So between -6 and 0, in the table, and here the key thing we have to use is that h of x is always increasing or decreasing in between consecutive values of x. Now, if we don't have this information, then all the table provides are the values at only like 7 different values of x. So here, in that case, probably the answer is not enough information because you cannot tell anything about monotonic just from the table. But since we have this key assumption, we know we can say a lot more. Say from -6 to 0, we see that h of x is going down from 2 to -0.5, then going down even more to -2, then going down even more to -3. So we know h is actually decreasing here. So let's go back down. So we know on this interval where we're finding the definite integral, we know h of x is decreasing. So again, just do it just draw it out really quickly if you'd like. H of x is decreasing. We're using the left Riemann sum. Is this underestimate or overestimate? It is overestimate. This is going to be larger. So this side should be larger than the left-hand side. What about in this case? Is h of x monotonic between 0 and 6? So let's go back up. Between 0 and 6, we see that h is increasing here from 0 to 2, increasing even more to 4. But now here's the problem. Now the h is now decreasing from 4 to 3. So h is actually increasing then decreasing between 0 and 6. So we don't know whether the underestimate is going to win out or overestimate is going to win out unless we have more information. So here, the answer to the final question, since h is not monotonic and we don't have a formula for h of x or anything, you really don't have enough information. So the answer is NEI.